Today we're going to take a look at synthesizing a lot of the concepts that we have seen up to this point into one concept, and that is to graph an equation. It's really a pain to graph an equation by calculating all the points all along the graph. And so what we're going to do is calculate the key points and asymptotes that we can use to get a very accurate picture of what the graph looks like. And so to help us with this goal, we're going to look at several tools that we have seen thus far of sketching curves. First thing we've seen that we can do is we're going to work to find any asymptotes. We have a vertical asymptote. I'm going to abbreviate it VA. We have a vertical asymptote from fractions when the denominator is equal to 0. And we also have horizontal asymptotes at the limit as x goes to infinity of the function. So we're going to find those asymptotes first. The next thing we're going to do is we are going to look for any intercepts. Mainly we'll be interested in the y-intercept because that should always be easy. And we find the y-intercept by making x equal to 0. Intercepts you find by making the other variable equal to 0. For the x-intercept, we make the other one equal to 0. We'll make y equal to 0, but we will only do that if it is easy to do. Sometimes it won't be easy to find these x-intercepts, and so we'll just ignore that step. Number 3, the third thing we're going to do is we're going to find the critical points. And those generally are going to be your local mins and your local max. Remember, we find critical points when the derivative is equal to 0. And finally, we're going to find the inflection points. That's when the concavity changes from a bowl that's filling up to a bowl that's spilling out. We'll find the inflection points when f prime prime of x equals to 0, or on the vertical asymptotes. Remember, vertical asymptotes, concavity can change as well. So we're going to find these 4 items, and then we will use these 4 items to help us graph the function. So let's take a look at our first example. Our first example is we're going to graph a polynomial. We're going to graph f of x equals 2x cubed minus 3x squared minus 12x plus 1. Finding all the parts, first we want to find any asymptotes. Well, since there's not any fractions, there really are no asymptotes. But rather, let's take a look at the shape of this graph. This is an x cubed graph. It's a positive x cubed graph, so we should know it comes in from the bottom. It might wiggle around, and then it's going to go out the top. So we at least know if there's no asymptotes, the shape of the graph should look something like this. Number 2, we're going to attempt to find some intercepts. First, the y-intercept is when x equals 0. And the nice part about when x equals 0 is the first term is 0, the second term is 0, the third term is 0. All that we're left with is the 1. And so we can tell really quick by just glancing, if we make x equal to 0, y must also equal to 0. Now for the x-intercepts, we put 0 in and we try and solve the 2x cubed minus 3x squared minus 12x plus 1, but that's probably going to be a little too difficult because we can't factor it, we can't solve it, so we're just going to ignore the x-intercepts for this example. We have the y-intercept at 0. Oh, nope, we have the y-intercept at 1 actually, don't we? 1. The y-intercept is 1. Number 3, we're going to find the critical points. The way we find a critical point is we make the derivative equal to 0. So let's find the derivative. F prime of x is equal to 6x squared minus 6x minus 12, and we make that equal to 0. Factor out a GCF of 6, leaves behind x squared minus x minus 12 equals 0. So continuing to factor, we have 6 times, oops, not minus 12, minus 2, sorry. 12 divided by 6 is 2. 6 times x minus 2 times x plus 1 equals 0, and so we find that x equals positive 2 and x equals negative 1. So now that we have our two values for x, we also need to find the y value that goes with them to help us graph. So we're going to plug 2 into the function and get an answer. And we're going to plug negative 1 into the function and get an answer. So we can find out the coordinates of those critical points. Now to help us out, we're going to go to our calculator. And our calculators are nice because if we hit the y equals button, we can type in the original function, 2x cubed minus 3x squared minus 12x plus 1, enter. And then we're going to type in the values we want that to solve. So we'll hit second table set and make sure after the independent variable ask is highlighted. If ask is not highlighted, scroll over to it and hit enter, and that'll highlight ask. And once we know that's highlighted, we can hit second table and type in the values for x we want the calculator to tell us. We're interested in 2, enter, and negative 1, enter. And so we see at 2, the point is negative 19, and at negative 1, it's 8. So negative 19 and 8. So we know on our graph the critical points are 2, negative 19, and negative 1, 8. Those are our two critical points. The last thing we're going to want to find then are the inflection points. Where does the concavity change from up to down or down to up? And an inflection point we find with the second derivative. We can take the second derivative of any point of this simplification. Probably the easiest place to take a second derivative is with the polynomial form. That's going to be 12x minus 6. And if we make that equal to 0, we're going to have something we can solve really quick by adding 6. 12x equals 6. Dividing by 6, and x is equal to 1/2, or 0.5. And so again, on our calculator, we're going to be interested in 0.5. And there y is negative 5.5. So the inflection point is 0.5 comma negative 5.5. So we have found now a lot of information. We have found an inflection point where the concavity is going to change. We found two critical points that are probably either maximums or minimums. We found a y-intercept. And we also know generally the shape of the graph because it's a positive x cubed. It's going to be going generally positive. So let's see if we can put all of this together, number 5, to actually graph the function. Now, because those y values on those critical points got pretty big, we're going to play with our size here. We're going to go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. These are going to count by 1. 1, 2, 3, 4, 5. Negative 1, negative 2, negative 3, negative 4, negative 5. Now those critical points went all the way up to 19 and change, so we're going to go up by 5s going up. 5, 10, 15, 20. So our scale is going to be off a little bit. -5, -10, -15, -20. And we'll graph what we know. We said there was a y-intercept at 1. We also said there was a critical point at 2, -19. So we'll go over to 2, -19. Should be -20 at the bottom, huh? So 2, -19 is about here. Let's make it blue, actually. And I'm going to label that's a critical point. So I know that should either be a local minimum or a local maximum. The other critical point that we found was at -1, 8. So at -1, 8, we've got another point. And again, that's a critical point, a local min or a local max. And we found our inflection point, where the concavity or the bowl changes direction at 0.5, -5.5. So right here's an inflection point. And so now we got to connect the dots in kind of a smooth curve. Like I said, the graph is going to come in from the bottom. And we're going to level off to hit that critical point. And notice the bowl right now is spilling. It's definitely a bowl that spills, but as soon as I hit that inflection point, I'm going to change the direction of my bowl to come up the other direction. And so this becomes my graph. Going through the points we found, using all the information we found, we've got our graph. Let's try and graph another one. Rather than a polynomial, this time we're going to graph a rational function. And this rational function we're going to graph, we'll start with a simple one. How about f of x equals x plus 1 over x? And the first thing we need to find are any asymptotes. We know we get an asymptote when the denominator, notice the denominator here is x, when the denominator is equal to 0. That is our vertical asymptote, at x equals 0. We're also interested in the limit as x goes to infinity of x plus 1 over x. And I want to remember that 1 over x, the limit of that is going to be 0. So really, what we have left, if I can switch pen colors, there we go. Really, what we have left is the limit as x goes to infinity is essentially whatever x is. So as x gets bigger, that's our new limit. This is what we call an oblique or slant asymptote, where y is equal to whatever's left here. Y is equal to x. We're going to have a slanted asymptote that it's going to get closer and closer to. We'll look at that in just a minute when we get to the graphing point. 2. Intercepts. If we wanted to find a y-intercept, we would plug 0 in for x, but that would make the fraction undefined. So that must mean there is no y-intercept. No y-intercept, because that would make the fraction undefined. To find an x-intercept, we make the whole thing equal 0. 0 equals x plus 1 over x. And if we multiply everything by x to solve, we get 0 equals x squared plus 1, because the x's reduce out. And if we subtract 1 from both sides, we get -1 equals x squared. Take the square root, and we can't take the square root of -1. It's I. We don't really graph I. There's no I complex axis here. So there's no x-intercept either on this graph. So number 3. Let's look then at the critical points. Now I've lost my function because I've had to scroll a bit, so I'm going to write it over to the right here just to remind us what it was. F of x was equal to x plus 1 over x. And if we're going to take the derivative of that, it's probably easier to think about that as x plus x to the negative 1, so that we can easily take the derivative. F prime of x is equal to 1 minus 1 times x to the negative 2. And if we make that equal to 0, remember a negative exponent means we bring that down to the denominator. And now let's see what happens when we clear the denominator. We multiply each denominator by x squared. We get x squared minus 1 equals 0. And that factors to x plus 1, x minus 1 equals 0. So x is equal to negative 1, or x is equal to positive 1. We have 2 critical points. To find the y values, we're going to do f of negative 1 and f of positive 1. And we'll do that on our calculator again. If we hit y equals, clear out the old function. This function is x plus 1 over x. And hit second table. We want negative 1, enter, and 1, enter. It's negative 1, negative 2, and 1, positive 2. So negative 1, negative 2, and 1, positive 2. We have our 2 critical points. Negative 1, negative 2, and 1, 2. 2 critical points. Finally, the last thing to find is the inflection points, which is when the second derivative equals 0, f prime prime of x. Scroll up a bit so that we can see f of x is at the top of our screen, f prime of x, sorry. The derivative of that is going to be positive 2 x to the negative 3 equals 0. And if we simplify that, the x to the negative 3 moves to the bottom. But we got another problem, because when we multiply by the denominator here, the x cubes are gone, and we get 2 equals 0, which it doesn't. So that means in this case we have no inflection points. Well, there might be one, actually. Remember, we had a vertical asymptote, so there might be an inflection change at the vertical asymptote. So we'll see if that works out. So let's review what we learned. We learned that we have a vertical asymptote at 0. We learned we have a slant asymptote at y equals x. That's a straight line with a slope of 1. There's no intercepts. We know we have 2 critical points and no inflection points. So let's see what this looks like when we try and graph it. Whoops. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. First thing we learned was that there is a vertical asymptote at 0. So we'll draw our vertical asymptote at 0. We also learned that there was a slant asymptote, y equals x. Y equals x has got a y-intercept of 0 and a slope of rise 1, run 1. So rise 1, run 1, rise 1, run 1, we end up with this slant asymptote. There were no x or y intercepts. There was a critical point, however, at 1, 2. Label that as a critical point. And at negative 1, negative 2. And that's a critical point. So from the critical point, if we're going to go towards the asymptotes, from the critical point towards the asymptotes, we end up with our graph of the rational function. Let's try one last example. Let's do another rational function, but we'll make this one look more rational. More like a fraction. We'll say the rational function f of x equals 3x squared over x squared plus 5. Looking for asymptotes? We get a vertical asymptote when the denominator equals 0, x squared plus 5 equals 0. But if we subtract 5, we end up with a negative 5, and we're not going to be able to take a square root of negative 5. That's an imaginary number. So we're going to have no vertical asymptotes. In terms of horizontal asymptotes, though, we can take the limit as x goes to infinity of 3x squared over x squared plus 5. And if you remember all the way back at the beginning of Unit B, we said the way we can take this limit is we divide each term by the leading coefficient. So we have the limit as x goes to infinity when we divide by x squared on each term. We get 3 over 1 plus 5 over x squared. Which is nice because the 5 over x squared goes to 0, and we're left with 3 over 1, or just 3. Equal to y is our horizontal asymptote. Number 2, x and y intercepts. The y-intercept is easy. We just make all the x's equal to 0. So we have 3 times 0 squared over 0 squared plus 5. And you see that ends up with 0 divided by 5, which is just 0. 0 is the y-intercept. The other intercept, if it's not too bad, is the x-intercept. And this one we can do. We make everything equal to 0. 3x squared over x squared plus 5. And that's nice because when we multiply by the denominator, x squared plus 5, we get 0 equals 3x squared. Divide by 3, x squared equals 0. Take the square root, and x equals 0 is the x-intercept, which we probably should have seen coming. If the y-intercept is 0, that's also on the x-axis as well. There may have been another one, though, so it was worth checking for other x-intercepts. Third thing we look for are critical points. Again, I've got the function off my screen, so I'm just going to rewrite it here so we remember that f of x is 3x squared over x squared plus 5. It's a quotient, so we use our quotient rule. F prime of x is low, x squared plus 5. D high, 6x. Minus high, 3x squared. D low, 2x. All over square the bottom, x squared plus 5, and away we go. Distributing through, we get 6x cubed plus 30x squared minus 6x squared over our denominator x squared plus 5 squared. Which is nice because 6x cubed minus 6x cubed is 0, so we really have 30x squared over x squared plus 5 squared. And we make that equal to 0 to find our critical points. Multiply by the denominator of x squared plus 5 squared to get rid of the fraction. And that leaves us with 30x squared equals 0. Divide by 30 and x squared equals 0. And so our critical point is where x equals 0. Now, based on our previous information about the x and y intercept at 0, we're pretty sure this is a 0, 0 point. But let's go to the calculator just to make sure. Hit y equals and clear out that old function. And it's also important to note that with fractions on your calculator, you need to put the numerator in parentheses and the denominator in parentheses. So we'll open up a parentheses, 3x squared, close the parentheses, divided by, open up a parentheses, x squared plus 5, close the parentheses, and you only need to type x once. Got it in here twice somehow. Enter. There it is. Second table. When x is 0, enter. Y is 0. So f of 0 is 0. So our critical point is at 0, 0. That's our critical point. One last piece of information to find then. That is number 4. We'll do it in black here. We need to find the inflection point. My f prime of x scrolled up a bit. So just to copy it down on here so that I know what it is, f prime of x we found was 30x over x squared plus 5 squared. So when we're going to take a derivative of this quotient, we'll just use the quotient rule with f prime prime of x. It keeps shifting on me. It doesn't want to scroll down so far. Oop, too far. F prime prime of x is low x squared plus 5 squared. D high times 30 minus high 30x. D low. The D low is a chain rule. It's 2 times x squared plus 5 times the derivative of the guts, which is 2x, all over the low squared, x squared plus 5 squared. To make this equal to 0 and solve is going to be a pain. Let's see if we can play with the algebra to make this a bit easier. Notice each factor, each part, there's two parts here, has a 30 and an x squared plus 5. A 30 and an x squared plus 5. I'm going to factor out that 30 and x squared plus 5. When I do, I'm left with an x squared plus 5 minus 4x squared, multiplying 2x, multiplying the 2x by the 2x is the 4x squared, and then the other parts were factored out. Over our denominator, x squared plus 5 squared equals 0. Which is nice because one of those x squared plus 5s can divide out with the denominator. So we now have 30 times, and if I combine like terms, x squared minus 4x squared is negative 3x squared plus 5 over x squared plus 5 equals 0. This is going to be a little easier to solve. Multiply by the denominator again to get rid of the fraction, x squared plus 5 gives us 30 times negative 3x squared plus 5 equals 0 times anything is 0. And we're going to divide by the 30 to get rid of that number. Now we have negative 3x squared plus 5 equals 0. And it's going to solve pretty quick from here. Add 3x squared to both sides. Divide by 3. And then take the square root. And when we do, we get plus or minus the square root of 5/3. Well, what is that? Calculators. Second quit. Second square root of 5 divided by 3 is about 1.29. So it's 1.29 or negative 1.29. which means we need to know what f of 1.29 is and f of negative 1.29 so that we can plug those into our graph. Y equals, we already have that in there. So second table, 1.29, enter, is about 0.75. And negative 1.29, enter, is about, again, positive 0.75. So both of them, 0.75. 0.75. So the inflection points are 1.29, comma 0.75, and negative 1.29, comma 0.75. Every problem, we're doing the same exact process. We're finding any vertical asymptotes or shape. We're finding x and y intercepts. We're finding critical points. And we're finding inflection points. Then we look over all of our work to see what we know. We know this time that there is a horizontal asymptote at 3. We know there's a y-intercept at 0 and an x-intercept at 0. It's really the same point, 0, 0. We know there's a critical point at 0, 0, so not only is that the x and y-intercept, but that's either going to be the minimum or the maximum of the function. We also know there are 2 inflection points. So let's put all of that together to make our graph. Okay, first, we found out that there was a horizontal asymptote at 3. Next, we learned the x and y-intercept was at 0. We also learned that that 0, 0 point is a critical point. Judging by the asymptote, it's probably a minimum. We also found inflection points at 1.29, comma 0.75, which is about here. That's an inflection point. And negative 1.29, comma 0.75. That's another inflection point. So the bowl's going to fill between those inflection points. But after I pass the inflection point, I need the bowl to change direction like it's going to spill out. And we end up with our graph approaching that horizontal asymptote. So again, to review what we're doing, we're bringing a lot of concepts together that we have been seeing over the course. We found our asymptotes and our shape first. Vertical asymptotes were the denominator 0. Horizontal asymptotes, we take the limit as x goes to infinity. If it's a polynomial, we should know the shape, where it comes in, where it goes out. Next, we found the intercepts of the graph. That's to find the y-intercept, we make x equals 0. That's easy. To find the x-intercept, we make y equal to 0, and it may or may not work out. If it doesn't work out nicely, we kind of ignore the x-intercept for now. That'll be okay. Next, we find our critical points. Critical points are when the first derivative equals 0. And then finally, the inflection points, where the second derivative equals 0. Put it all together, and you have a graph. Take a look at the homework. We will see you in class tomorrow with questions.